Okay, the next type of nuclear decay I'm going to talk about is beta decay. Again, nuclear decay is changes in the nucleus of an unstable atom. So it's breaking down, the parent nucleus is breaking down to make a new daughter nucleus or a new isotope that is more stable. And beta decay is another way that this can happen. So in beta decay, this is what happens. A neutron turns into a proton, and an electron is going to leave the atom. So you have this parent nucleus, and we have an electron which leaves the nucleus, and we actually call this electron a beta particle. And our neutron turns into a proton, and that changes the nucleus, okay, to make it more stable. So a neutron turns into a proton, and an electron leaves the atom. This electron is called a beta particle. Now, there is two ways you can write a beta particle. This little b, oh, look at that. Let me see if I can change that. There we go. Okay, so two ways to write a beta particle. Bright thinker writes it like this. There is no mass number, and the -1 tells you it's got a negative charge, and you've got this funky little b. That is one way you can represent, okay, a beta particle. Another way, and I have always done it this way, this represents a beta particle. I've always written it E0 minus 1. Or you can put the minus on the other side. Minus 1. So you get to choose. I'm used to doing it this way, but Bright Thinker likes to represent the beta particle like this. So when it comes to doing equations, better move that right there. The mass number of your parent isotope does not change in the product. Our atomic number, however, changes. It goes up by 1. That makes sense because a neutron turns into a proton. So our mass number doesn't change because the mass number is the total neutrons and protons in the nucleus. So just the fact that a neutron changes into a proton is not going to affect the mass number. However, it is going to affect the atomic number. So our atomic number is going to increase by 1. Again, we have our reactants and we have our products. In beta decay, you have one single reactant. Okay, it's some sort of parent isotope, like iodine 131. And then your products, you're going to have two products. You're going to have a new isotope, which is our daughter isotope, and a beta particle, which is the electron that leaves the atom. So let's look at how we do these. I do these exactly like I do the other ones. You need a periodic table. So I'm going to start with this example here, iodine 131. Okay, so we know there's only one thing on the on the reactant side, so I'm just going to draw my produces line. I know for a fact this breaks down through beta decay, so I am going to draw my beta particle, and I prefer the E minus 1. And a daughter product. Now I have to figure out what my daughter product is. I know the mass number doesn't change, so I'm just going to write my mass number 131. However, my atomic number goes up by 1, so 53 is going to turn into 54. Now I'm going to go, ooh, that's terrible. There we go, 54. So now I'm going to go to my periodic table, and I'm going to find the element that has atomic number 54, and that's going to be xenon. So Xe. So when iodine 131 breaks down through beta decay, it will produce a beta particle that leaves the atom and a new daughter product, which is xenon 131. So let's look at these other two here. This is strontium 90. I know it breaks down through beta decay, so I'm going to draw my produces line. A beta particle is always made, so I'm just going to start with that. E0, 1 minus, plus my daughter product. So now, my writing's terrible. So now I have to do a little bit of math. My mass number doesn't change, so I'm going to carry over the 90. My atomic number goes up by 1, so that makes it 39. Now I'm going to go to my periodic table, and I'm going to figure out what element has atomic number 39, and that is yttrium. So capital Y. This is my beta particle. This is my new daughter product. More stable isotope than my starting isotope. Nitrogen 13, again, I'm going to draw my produces arrow. I know it breaks down through beta decay, so I'm going to draw my beta particle. And I have to figure out my daughter product. So mass number stays the same. Atomic number goes up by 1. So element with atomic number 8 is oxygen. So it's oxygen 13 that is produced. And that's beta decay. Last one is called gamma decay. These ones are super easy. So gamma rays are to the furthest end of the electromagnetic spectrum. So the electromagnetic spectrum has got 7 different types of radiation or energy. They move through space and a medium through transverse waves. So this is a transverse wave. The longer the wavelength, the less energy that's carried. The shorter the wavelength, the more energy is carried. So radio waves have very little energy that's carried in their waves. Gamma rays have a whole lot of energy that's very dangerous. Gamma rays, of course, are produced in the core of the sun, are produced when an atomic nuclei breaks down. They're used in radiation for cancer. They're very strong. They can alter the DNA in a biological cell. So the idea behind gamma decay is it's radioactive decay in which an unstable excited nucleus, releases a gamma ray and produces a more stable nucleus. The equations are super easy, okay? There's not much going on here. So gamma ray is usually, in our equations, usually is represented like this. You kind of have this funky Y and a 0 and a 0. So there's no mass number, there's no atomic number because it has no mass to it. It's just energy. So that's kind of crazy looking. So it's like a Y and a 0 and a 0. So what happens is this. So radioactive decay in which unstable excited nucleus emits gamma radiation and forms a more stable nucleus. So what this means, the M is called a metastable excited, okay? So M represents metastable. This basically means the nucleus excited. That's it. So anytime you see an isotope written like this, if you see the M, that means that the nucleus is excited. It is very unstable. It's got too much energy and it needs to release some energy. So M means metastable. It just means the nucleus is excited. So we're going to draw these. We're going to do these equations just like we did before. I'm going to do the produces arrow. What happens is this metastable isotope is going to release a gamma ray and it is going to produce a more stable or relaxed nucleus. So this is how you write the equations. You write your gamma ray plus, we're going to write the exact same, because gamma radiation is energy, it's not matter. So there's no changes in matter going on here. So our new stable isotope is technetium 99, atomic number 43. So the only thing that changes from the product, from the reactant to the product, is the M goes away because the gamma radiation leaves the nucleus and produces a normal or more stable isotope. Super easy. Again, I know this breaks down through gamma decay, so it's going to produce a gamma ray and a more stable isotope of iodine 125, atomic number 53. Okay, that is it. Hope everything's going well. Keep an eye out for information on the final, and let me know if you guys need anything.